All right, this is going to be great. I cannot wait to build a calculus for fields, to do differentiation, integration, all that good stuff. But we have to go slow. It takes time to build calculus for things other than scalar fields. First, it's going to help to make sure that all the fields that we wind up working with are continuous and maybe differentiable. You know what that means, right? Well, maybe not. What does continuity mean? I like to think in terms of inputs and outputs. Continuity has something to do with the notion that nearby inputs imply nearby outputs. But what does that really mean? Well, let's think for a minute. Certainly, we know when two scalars are close, right? We've been working with that all throughout calculus. What does it mean for two vectors to be close? Well, it kind of makes sense. Two vectors are close if and only if all their entries are close. Good, I can work with that. That same principle works for matrices. Okay, I can work with that. What about things like, let's say polynomials? Can you say what it means for two polynomials to be close? What about other things? Well, that's a little bit outside the bounds of this course, but if you're curious, then I guess it must be bonus time. There is so much more to the notions of continuity and smoothness for fields and functions that you could learn about. For example, let's say that you want to take a little bit more mathematics after you're done with calculus. You might take some courses in real analysis, in which you'll learn about metric spaces. In a metric space, every pair of points has a well-defined distance, a distance that is not necessarily Euclidean. So you can talk about the distance between two polynomials, or the distance between two DNA sequences, or the distance between two data sets. And having that kind of structure is going to be really useful for talking about things like continuity of functions. But that's not all, because there are spaces, topological spaces, where you don't have a well-defined notion of distance between them. Nevertheless, you can still encode proximity using something called a topology. This is really useful when you're talking about things like abstract networks, if you're talking about things like, phylogenetic trees for organisms, all kinds of situations where you don't have a notion of distance. Nevertheless, in these settings, you can still make sense of things like continuity of functions or fields, and sometimes differentiability. Now, we're not going to go there. That's way outside the bounds of what we're doing. We're going to assume that everything in sight is as continuous and as smooth as we need it to be.